Okay, welcome back. For me it's now the first day of term 2, so Wednesday. I've already seen most of you today, but some of you I haven't caught up with. So I'm starting the video lessons now for topic 10. So hopefully topic 9 is becoming comfortable. There's some tough bits with the simple harmonic motion and the waves. But I'll continue to go through this. So this is topic 10, fields. It pretty much just looks at gravitational fields and electric fields, which we'll find are very, very similar. And so we'll look at there's a lot of stuff in the data booklet about that, but we'll work our way through that. What we've got on the board at the moment is, I think, stuff you already know, but it then leads into trickier stuff as we get through it. Okay. So, look at gravitational fields and electric or electrostatic fields. So we're talking about fields around a point charge, or around a charged object, or indeed between parallel charged plates. For gravitational fields, we're mainly talking about the gravitational field around a planet, a star, and at or near the Earth's surface, effectively, even though it's pointing towards the centre of the Earth, that's pretty much parallel and it's just vertically downwards. Okay, so gravitational field is a region where a mass will experience a gravitational force. A gravitational force will always be one of attraction. So two masses will always attract each other, whereas two charges might attract or might repel. So a gravitational field is defined as a region where any mass will experience a gravitational force. And that becomes an important definition. We'll come on to that in a moment. An electric field, similarly, is a region where a charge will experience an electric or electrostatic force. So I keep putting both of those, they're sort of interchangeable. Electric force, electrostatic force. Electrostatic literally means static, not moving, a stationary charge. But it could well be moving. So, you'll find that as we have a charged particle moving through between parallel plates, it will be deflected up or down. It might get bent by magnetic fields as well, but we'll come to that in the later topics. Okay, so the gravitational field is the force per unit mass, F over m, so Newton per kilogram. We talk about the Earth's gravitational field as 9.8 what? Well, 9.8 metres per second squared is the acceleration due to gravity at or near the Earth's surface. 9.8 Newton per kilogram is the magnitude of the Earth's gravitational field at or near the Earth's surface. So the unit is Newton per kilogram. Now these two definitions here, I'll go through this one and then go through the definitions. Electric field similarly is the force per unit charge. Okay? And its unit therefore is a Newton per coulomb. Alright, so remember with those units, Newton per kilogram, Newton per coulomb. Okay, so these definitions here, they come up pretty often, particularly just in paper 1, the multiple choice one. So the gravitational field is defined as the force per unit mass, so force divided by mass. So, if I've got me, 90 kilograms, the weight force pulling down on me is 900 newtons. So the gravitational field is the force divided by the mass. So that's 900 newtons divided by 90 kilograms would be 10, or 9.8 newtons per kilogram. So it's the force divided by the mass, it's the force per mass. There are 10 newtons pulling down on every kilogram. That's the force per kilogram, acting on a small or point mass. They want you to throw that into the definition because, again, if you've got two large masses, how far apart are they? Well, the front of this one, is quite close to the front of that one, but the back of that one is quite far from the back of that one. And so, we normally talk about masses as being point masses, all right? Or on a small or test mass, sometimes they'll say as well, all right? So, and exactly the same for the electric one. The electric one is the force per unit charge acting on a small or point or positive charge. We could throw in positive test charge there as well. I've got a charge object here and I bring in another charge here. If I bring another small charge here, then I know it's going to get repelled. I can work out what the force is on this small charge, so the force per unit charge. It's not going to be a coulomb, it's going to be much less than a coulomb. So remember those definitions. It's probably worth putting a box around those definitions, each of those, because they come up really often. So make sure you are able to use those. And similarly, as we get into potential and potential, so there's a few other things we've got yet to define. So here's the Earth. The gravitational field, of course, is a radial field. Radial, like a radius towards the centre or away from the centre, in this case towards the centre. If they're asking you to draw the gravitational field lines, draw them carefully and make sure they're nice and straight. I've got these equally spread out here. I've tried to do one at every 45 degrees there just to, so it's easy to do this and this. And the direction of that field is inwards because the direction of the force on any mass will be inwards towards the centre of the Earth. We know that G is equal to F over M. The gravitational force, Newton's law of gravitation, is that F equals gmm on d squared or x squared or r squared, whatever you like. Gmm on d squared per mass, so the m's cancel out, well therefore the gravitational field is equal to gm on d squared. If you put in the numbers for the Earth, the mass of the Earth and the radius of the Earth, and g, the universal gravitational constant, then you'd find that that was 9.81 at or near the Earth's surface. Note that it's an inverse square law. As the distance doubles, so if we go from here to here, that's the radius of Earth. If I went the same distance again, the gravitational field here, so the radius of the Earth is 6,400 kilometres. If I went another 6,400 kilometres above the Earth's surface, so 12,800 from the centre of the Earth, then the distance would be twice as much, the gravitational field would be a quarter as much, so the gravitational field there would be about 2.5 Newton per kilogram. All right? And by the time we get out here, if we're 10 times the distance, there's 10 times that distance, we'd have 100th of the gravitational field. So not 10 metres per second, not 10 Newton per kilogram, not 1, but 0.1, 100th as much, 0.1 Newton per kilogram, not much at all. Note here that the magnitude of the gravitational field is greatest where the field lines are closest together. So field lines are relatively close together here and further apart here. You might say, hang on, the gravitational field, there's nothing out here because there's no field lines. Well, I could have drawn in more field lines, but clearly the field lines are further apart there and closer together here. Remember also that it's a three-dimensional thing, the field lines coming out like that and into the page, so it's a spherical radial line thing. But that becomes an important thing as well, not just for gravitational field lines around the Earth, but particularly for electric fields, and I'll get onto that in a moment. So, exactly the same situation. The two things, gravitation and electrostatic, are so similar. And, we've got a whole set of formulas that follow the same pattern. And, by the end of this chapter, we'll have, hopefully, all that together. So, here's the electric field around a positive charge. We're going out, out, out. Remember, the electric field, the direction of the electric field is defined as the direction of the force on a positive test charge. It's okay there, but, if, for example, I had some charged plates, the direction of the electric field there is the direction of the force on a positive charge. Away from positive towards negative, the direction of the electric field will be like that, but we'll draw that up shortly anyway. Okay, so it's defined, the direction of the electric field is defined as the direction of the force on a positive charge. Okay, away from positive, here towards negative. So that diagram is essentially exactly the same as that one. The electric field is defined as the force per unit charge. The force, just like this is GMM on d squared, this one is KQQ on d squared. The Coulomb's law of electrostatic force. So this is KQ1, Q2 on d squared, or KQQ on d squared divided by Q. The little q's cancel out. We're left with KQ on d squared. Again, it's an inverse square law. At double the distance from a charge, the electric field would be a quarter as much. And so the same charge placed there would experience a quarter of the force. And exactly the same, the magnitude of the electric field is greatest where the field lines are closest together. That becomes important if you've sort of got an odd-shaped object with charges on it. You know, it's not going to be a nice spherical one, and we'll probably find that the field lines are like that, and the magnitude of the field is greatest where the field lines are closest together. That looks like this bit here, and often around a point. You know, you've seen with that Van de Graaff generator, you know, that if you put a pointed object towards it, it's more likely to spark because the electric field becomes greater there. So, you know, where the field lines are closest together is where the magnitude of the field is greatest. Okay? So, you know, both of those are significant and they both lead on to what we're doing next. Okay. In both cases, the G field and the E field is zero at what? Well, they would be zero at infinite separation, at an infinite distance. However, you know, they become, you know, obviously smaller and smaller, and so, you know, 6,400 kilometres the radius of the Earth, 10 times that, so 64,000 kilometres from the centre, so what's that, 58,000 kilometres above the Earth's surface, it's 10 times the distance, so 100th as much. Gravitational field is pretty small out there, and if you drop something out there, it would accelerate towards the Earth, but with a really low acceleration. The acceleration would be the same as the gravitational field here. It would accelerate at 10 metres per second squared, 9.8. Way out there, it would accelerate at 100th as much, 0.1 metres per second squared. It would accelerate at a very slow rate. Okay. Alright, we know that, like force, gravitational field and electric field are both vector quantities. So, you know, what that means is that the gravitational field or the electric field for any combination is the vector sum of the two. Let's go through that. are both vectors. What does that look like? Are both vectors. The overall field at any point is the vector sum of the individual fields. So here's the Earth, and here's another Earth that was the same. If we were halfway between, then whatever that distance was, there would be a gravitational field towards Earth 1, there would be an equal gravitational field towards Earth 2, and so the overall gravitational field at that point would be 0. If we were at a point much closer to here, then we would have a gravitational field towards there, a much bigger gravitational field towards there, not necessarily touching the surface there, let's deliberately draw that so it's not, but it's much bigger because we're much closer. If those masses, assuming the masses are the same, then the overall gravitational field would be, for example, -2 plus 20 or something, which would be 18 in that direction. All right? Perhaps a more reasonable situation is the moon. All right? If we were halfway between the Earth and the moon, we'd have a gravitational field towards the Earth, and we'd have a gravitational field towards the moon. Since the gravitational field is equal to gm on d squared, d is the same for both of those, but that's a much smaller mass. Therefore, we've got a much smaller gravitational field, and so the net gravitational field would be that one plus that one, which would give us that as a resultant. We can find a point fairly close to the moon where we are closer here to the smaller mass. There's the gravitational field, there's the gravitational field due to the Earth, and so we could get the point where the gravitational field was 0. And certainly astronauts on the way to the moon, well, the gravitational field is pretty small anyway because you're a long way from the Earth and a long way from the moon for most of that journey there. But around this region here, you've really got 0 gravitation. Mainly what we see is astronauts in orbit around the Earth, and the gravitational field is not 0 there, but you've got the effective gravitational field. You've got apparent weightlessness because you are going around in the circle. In the case of centripetal acceleration, and so the acceleration is caused by the gravitational force at that point, and so everything around you is accelerating the same. It's like if I was in a falling elevator, as I'm falling down, everything would be falling together. You say, wow, this is amazing, I could drop the pen and it would just stand there with me because we would both be falling, accelerating together. Of course, then we hit the ground and we're all killed and the pen hits the ground. But exactly the same for a satellite in orbit. As it goes around, it is accelerating, and everything is accelerating the same. And so if you hold a pen out there, it will keep accelerating with you. And so as far as you're concerned, it's not moving relative to you, and so you experience that apparent weightlessness. There is no real down. Okay, so. That's when we're like that, but what about if we had, we'll stick to the Earth and the Moon. If we were here somewhere, then we're going to get a gravitational field towards the Earth. We're a bit closer to the Moon, but it's much smaller, so I think we're going to get a smaller gravitational field there. The overall gravitational field would be the vector sum of those two, so that one plus that one gives us, we might put it in a different colour, the overall gravitational field, that one plus that one would give us something like that. Alright? And so the same thing applies with charges. Let's have a couple of charges. We'll have equal charges, so I'll have a positive charge here and a negative charge here at this point here. We're equidistant from both of them. So the gravitational field is away from the positive, if they are equal charges, then the magnitude of the electric field would be equal. So I've got an equal one towards there. The overall field would be the vector sum of those two, so that one plus that one. And of course I can add in whichever order I want. And the resultant would be this one here. Alright, so you most likely get something where you're between the two charges. For example, let's have a look. Let's do one. I've seen this question where you've got, say, plus 3 coulomb and minus 1 coulomb. Let's say A, B, C, and D. Alright. In which region, A, B, C, or D, could the electric field be 0? In which region could the electric field be 0? Over at A, my electric field is away from there and towards there. It's a smaller charge and I'm much further away. So there's no way it can be 0 out here. That away from the plus 3 coulomb is always going to have a bigger effect than the minus 1 because it's a smaller charge and we're further from it. Okay, at point B, I'm away from the plus 3 and I'm towards the minus 1. Well, that's never going to be 0 because they're always in the same direction. At point C, I'm away from the plus 3, I'm getting further away, I'm towards the minus 1. They could be equal, but they're in the same direction, so that's not going to be 0. Over in region D, I'm away from the plus 3, and I'm towards the minus 1. So I'm in opposite directions, as this was, but this is the bigger charge, and so at some point out here, the effect of this bigger charge and I'm always going to be closer to this one, those two effects could cancel each other out, and we can work that out numerically. But region D is the one where the electric field somewhere in region D could be 0. Okay? And I've seen that question lots and lots of times. Okay. So I think we now need to move on to, electric fields, gravitational fields are vector quantities, you add them vectorially. Hello. So I'm just videoing chapter 10, but that's alright, we'll see you back here in a little while anyway, so 1:30 for physics, yeah.
Oh, okay. Oh, 1:30, okay, I just realised.
You can leave your stuff there, that's alright. Yeah. Okay, so the next bit is about potential energy. So we've already talked about, when you're familiar with potential energy, the gravitational potential energy is equal to mgh. Well, that's true as long as you're only a small distance from the Earth's surface. If you want to send a rocket to the moon and you say, oh, we'll just use mgh, then you're going to be a long, long way out. So really, yes, but only for small distances or close to the Earth's surface. Okay? Because really where potential energy comes from is that delta EP equals work done equals force times distance. Okay. Now again, that's not totally true. it's actually the area under the force distance graph. If the force is constant, so you know, if this pen is a kilo, there's 10 newtons pulling down on it, there's still 10 newtons pulling down on it, 9.8. The force essentially hasn't changed. But if I go from the Earth's surface to here, then the gravitational field has changed, and so therefore the force on any mass has changed. So what does the force distance graph look like? Well, I could say that it's like this. It's an inverse square law. Or I could have said like this. Either of those is a reasonable way of showing that. So that's the force. So again, we started off with a couple of masses, and that's fair enough. So the force on two masses is attractive. Does that mean it's a negative force? Well, you could interpret it either way, but it's certainly decreasing. Let's just stick with that. But again, it could be just as good the other way. If here's the Earth's surface and I'm going from here to here, then the work done is essentially mg times h. Alright? But if I'm going from here to here, then the force isn't constant, the force is changing. And so, you know, what I want is the area underneath that. And how do I find the area under that graph? Well, I can count up squares or I can integrate. Okay? So this equation is that F equals GMM on R squared, D squared, we'll stick with it. But R sounds like a radius, and you know, we're not necessarily just talking about the radius of the planet, we're talking about the distance from the centre of the planet, of the mass. Okay, so the work done equals the change in potential energy equals the integral of F d. Well, that's why I wanted to use R. I'll stick with R because otherwise we've got the integral dd. So GMM on R squared, but R is not necessarily the radius, it's the distance from the centre. Alright, equal of F dr, so that becomes the integral of GMM on R squared dr. What's the integral of, so it's GMM times the integral of 1 on R squared dr, which is GMM times integral of 1 on R squared, negative 1 on R, equals negative GMM on R, plus C. Yeah. So, you know, you can't, you know, when we're using MGH, where is the zero of gravitational potential energy? Well, wherever we want, at the Earth's surface, you know, at the table, at the floor, at the roof, and I drop things from the roof or onto the roof, or wherever I want. We need to be a bit more careful with this. If I'm going from the Earth to the Moon, where is the zero of gravitational potential energy? At the Earth's surface? Could be. At the surface of the Moon? Could be. Halfway between them? So, yeah, it becomes a bit tricky. So what we do is we define the zero of gravitational potential energy as being at infinite separation. And so what that means then is that C becomes zero, and so the gravitational potential energy is negative GMM on R. What does that mean? If we're at infinite separation and the potential energy is zero, two ways of looking at that. either I'm lifting up this pen and I'm doing work on it and I'm getting it all the way to infinity, and by the time I get to infinity its potential energy is 0. Alright, well that means that at any finite separation the potential energy must have been negative. Alternatively, there's that mass, that pen, out of infinite separation, it will fall towards the Earth. As it falls towards the Earth, it gains kinetic energy, it loses gravitational potential energy. Well, there was 0 out there. As it loses some, it becomes negative as it gets closer. So, you know, it's a bit of an abstract concept to think that gravitational potential energy is negative, but it will be negative for any finite separation. If I want to get this pen, if I want to get this rocket to infinity and back to infinity, then I need, you know, whatever its potential energy is there is negative 1,000,000 joules. I've got to add 1,000,000 joules to it so that its total energy is 0 and it can get to infinity. So it does make good sense, but it can be a bit tricky to understand to start with. So, way out at infinity, well it's not infinity, but you know, keep on going, the potential energy is 0. Here we're negative a bit, here we're negative a lot. Okay? So, at any point, EP equals negative GMM on R. So there's our formula for for gravitational potential energy, negative GMM on R. Exactly the same for charges, because again we've got this same inverse square curve for the force, and the work done is just the area underneath that. So it'll be done in exactly the same way, and so we get that EP equals K Q on R. Plus or minus, well, you know, with masses it's easy because two masses are always going to attract each other. Infinite separation, 0. Fall together, lose potential energy, so it becomes negative. If you've got two charges, two opposite charges, 0 at infinite separation, they'll fall together, and so they will lose potential energy, and so the potential energy will be negative. Right? But if I've got two charges the same, they're out at infinite separation, I've got to do work to bring them together, and so their potential energy will be positive at any finite separation. And similarly, if I've got two positive charges here, they fly apart, they lose potential energy as they fall apart and gain kinetic energy, and so they lose potential energy to get to 0, so therefore it was positive at any finite separation. So for two opposite charges, EP will be negative. For two like charges, EP will be positive. I think we normally write it as plus or minus KQQ on R. You know, basically if one's positive and one's negative, then you'll get your negative answer there. If they're both positive or both negative, you'll get your positive answer there. But it's more important that conceptually that for two like charges, as you push them together, you know, again, the definition is always the same. For two masses, for two opposite charges, for two same charges, the potential energy is 0 at infinite separation. Right? So we've got that there, so EP is that, and EP equals plus or minus KQQ on R. Very similar things. This leads us to lots of different situations, but I reckon I'll stop there now because I've got a class coming in shortly. So that hasn't really covered all of 10.1. It hasn't talked about electric potential. We've talked about potential energy, but not potential. And so we'll go on with that maybe later today after I've got this class.